So for today I want to talk about first the concept of span, then concept of distance, and from there we are going to talk about norm, or if you wish length or size or magnitude of a vector. Then we are going to talk about the angle between vectors. That's going to bring us to the concept of dot product. This would be the angle definition. We are going to talk about perpendicular vectors. Then we're going to talk about length of a vector, in terms of dot product. I'll have a brief review of a topic from trigonometry. Over there it's called law of cosines, which we are going to use to prove a major theorem here, which is going to give dot product, same one we are looking at here, but in terms of components. Once we have that, we have just two more topics. One is the topic of unit vectors and the topic of projections. Okay, so long laundry list if you wish, but they are all intuitive ideas. Each of them by themselves is very straightforward and clean cut, and so we might not have that much of a hard time following through. Okay, let's go through these things one by one. What's the span? Well, it's a word you use in English. In mathematics, the concept of a span is kind of a space that is supported by a bunch of vectors. Let's start with the span of a single vector. Vector all by itself. So suppose I have some vector, and here is some coordinate plane for my activities. First of all, I transfer the vector that I have to the origin here. So I just move it over parallel to itself to this location. Then I think about all of its multiples, that is, perhaps doubling this thing, perhaps tripling it, perhaps multiplying it by minus 1 and minus 2 and so on. And then even beyond that, I might multiply it by half or 2/3 and such. Consider all multiples of this vector, where all multiples form a line. The line that is indicated by a vector and passes through the origin is simply called the span of that vector. So it's a line through origin that's parallel to the vector you are interested in. Line through origin. So we are talking about span of a vector V is a line through origin which is parallel to V. For this whole thing to make sense, of course, we must have a vector of some size or magnitude. Otherwise, however you multiply it, you still get a 0. So a vector, a non-zero vector, if you're considering a non-zero vector, all multiples of it constitute a line. That line is called the span. So we are going to write it as span of a vector v. Another way of describing the same thing is to say, okay, take a vector v, multiply it by any number you wish. That number multiple is traditional to call it just t or something. Look at all such things. When you want to say look at all such things, you make a curly bracket and then say t is any number. So how is this going to be read? Span of v is the following set. That set made out of t times v, where t can be any real number. That becomes a span. Okay, that wasn't all that exciting. Going on to the next idea is, what if I have more than one vector, span of say 2 vectors? So in this case, for simplicity's sake, we start in 2 dimension. Suppose you have some vector v and some other vector w. What we have in our mind is all such combinations. Those combinations are called linear combination of several things. Means you are taking those items, multiplying them by some number, like multiply this thing by r and multiplying this thing by s, and adding them up. This is an example of a linear combination. For example, v plus w itself is a linear combination. Okay, so here are some examples of linear combination. V plus w is just a nice linear combination. If you take 2v plus w, that's a combination. If you take v plus 3w, that is a linear combination. Minus v plus 5w, that's a linear combination. Perhaps you just pick v and 0 w's. Okay, so if you have no w, maybe you're picking 3 of these things and no w's. Or perhaps you are not picking any v's, but you're taking some w's. So anything goes. And in fact, these things don't have to be whole numbers either. So you can have 3/5 of v plus 11/9 of w, or whatever. So r and s that we are writing here are just numbers. Any such thing is called a linear combination. Now, span of 2 vectors is a set of all such things you could make. So if you say span of v and w, that is set of all linear combinations of v and w. Just to see what is involved and not to get sidetracked with too much detail, let's first rely on the linear combinations that are made by whole numbers. That's going to be a little bit easier to visualize before we go further. So suppose I have these 2 vectors. Okay, so I have some vector v and some vector w. We said we want to make all linear combination. One basic thing we could make was to just add v and w. That's going to be this point. Is that right? Now, how about 2v? Where is 2v? I'm just putting a dot so that the picture wouldn't get too crowded. Really, you have to draw the whole arrow. But 2v is going to be about here. Is that right? And then say 3v. How about 2w? That's a linear combination that is acceptable to us. 3w. How about 2v plus w? That's going to be about here, is that right? That is 2v plus w. How about 3v plus w? Well, that's going to be kind of like here. And so on. V plus 2w. V plus 3w. What does this thing look like? It looks like a tile work, is that right? Except that the tile is not a regular square or something, but if you just make up your lines here, these are lines that are parallel to your V. These are the lines that are parallel to, W. These are lines parallel to your V. And as if you have placed a bunch of parallelograms there and filled up the whole page with them. In fact, you could go the other way as well with the negatives. Okay, so such spots would have been also feasible to arrive at by taking some negative multiples and such. So when we think about all linear combinations of two vectors, we think about some sort of something like a lattice in space, if you wish. It kind of reminds you of a beehive or something like that, but well, beehives are made out of hexagons. This thing kind of like maybe these grills or the tile work under your feet and such. Now, if I think about all possible linear combinations, not just a whole number, but if I allow, for example, half of V and 2/3 of W and all such combinations concerned, then what spots are going to be covered?
Everything in between.
Yeah, if everything in between of these things are going to be fair game, like half of V and 2/3 of W, and combination of those two could be used to arrive at certain spot. Or 2/3 of V plus 3/7 of W, that would be, say, another possible linear combination. If I consider all possible linear combinations, not just the whole integer multiples, like this point will be okay, this point will be okay. So what does it look like? That I'm going to end up covering the entire plane, is that right? So I can arrive at any point, any place. So with two items in a page, this is not very hard to visualize. But suppose I have these two vectors, these red pen and black pen, these are my vectors. How would you describe set of linear combination of these two? What geometrical shape or physical shape? Yeah, it would be a plane, YXY plane. These are just two arbitrary vectors in 3 dimensions. So we want to describe the linear combination of these two. Suppose I'm holding them, my thumb holding the start of these two vectors. Suppose that's the origin. The linear combination of these two turns out to be what? It's going to become just the entire page that is resting on top of these two vectors. Is that right? Is that understandable by everybody? That is, if I take this red vector and extend it, and the black one and extend that one, and consider all summation of these two, I'm just going to cover the space that is the page or plane resting on top of these. I have no way of getting out of that plane. I'm restricted to that plane. So let me just try to draw something like this here. So if you are in 3 dimensions, and I have two vectors here, one of them, say, is this vector V, and the other one is vector W going in a different direction, then linear combination of these two is going to be the plane that is resting on those two vectors. Here's a way of trying to approximate that plane. So this is, we are hopefully trying to convey notion of a plane in space. Of course, that plane extends throughout the entire space, but we just can draw a little bit of it. This plane is equal to span of the two vectors v and w. So in some sense, you say if you have a bunch of vectors, what portion of space can they support? What can be covered by these? Okay, there will be a bunch of exercises you are going to practice by drawing vectors and trying to convince yourself of what the span of a certain vector is going to be. Now, there are certain kind of, if you wish, pathological or extreme cases. Suppose I have a vector v which is just a zero vector. What's the span of it? Well, set of all linear combination of that thing by itself, it's not going to go any further than the origin. It's just the point. We are stuck at the origin. We don't have anything else to play with. However, multiples you are going to consider, you're not ever going to get out. Now, suppose I have the other extreme case, that I have a vector v like this, and my vector w turns out to be, say, double of v. Is the linear combination of these two things a plane? Excuse me, is the span of v and w, like here I had a v and w, the span of it became an entire space. But let's consider the following situation, that I have some vector, this is my vector v, and accidentally my vector w happens to be one such thing. Is the span of these two guys an entire plane? Is it? So if I have one vector, a multiple of another one, well, however linear combination of these two things I consider, what do I get? I get stuck on that line, is that right? I can never get out. This becomes the span. So we see the following interesting situation. Sometimes the span of two vectors becomes a large item, in this case the entire plane, and sometimes having a secondary vector doesn't really help us. Our span, it looks like span of just one vector. What is special in this case? Special is one of these vector itself was a multiple of the other one. The w was in fact belonging to the family of these green vectors. It wasn't really something new for me to give me a new direction to travel in. That was same old direction, so I'm never going to get out of this line. So we want to distinguish between two situations. These two vectors looking like each of them going a different way, and these two, both of them headed in the same direction. We are going to have some terminology for this thing later on, but right now we're just getting our feet wet. These two vectors are going to be called linearly independent. Okay, independent means they are going, each of them going a different way. None of them is copying the other one. None of them is redundant. If you remove one of them, your structure does collapse. The whole span cannot be supported. This kind of a situation, when one of them can be written as a linear combination of the other ones, or in this simple case, one of them is simply a multiple of the other one, these are called linearly dependent. Now, from having taught this course before, I know that somehow, for some reason that kind of baffles me, students get confused on this notion of dependence and independence. I don't know exactly what the reason is, but you need to read that section carefully and explain it to yourself and write the terminology and practice the word until you are comfortable with it. Okay, so it's part of your you have a declaration of independence. So this word has to make good sense to you. Somehow it doesn't for some reason. So this V and W, two vectors going obviously different direction, they are independent from each other. If one of these is double of the other one, or triple of the other one, or minus 5 times the other one, in that case we call them linearly dependent. For two vectors, it's easy to tell if you are dealing with this situation or you're dealing with that situation. But if you had many vectors and you are in some high dimension, the issue becomes a tangled one. It's not so trivial to say what's going on. We are going to spend some time on that issue later on. Okay, moving on to the next topic for today, we are going to talk about distance. Let me remind you of this from high school, college algebra classes. You had something called distance formula. This is exactly the same thing. Just quick review. If you have some point with coordinates A, B, and some other point with the coordinates C, D, by the distance of these two, we could mean the length of this line. Well, how do you find that length? The prime tool for measuring length is the most famous theorem of mathematics, which is what? Pythagorean theorem. So you try to make a right triangle here. The easiest way to create such thing is to draw lines parallel to your coordinate system. Now you have this showing up as a leg of a right triangle. This is the other leg of the right triangle. This is the hypotenuse of this. The three of them are connected based on a very simple formula, and that's all we are practicing here. So we say this leg, I'm going from point A to point C. So how long is it? C minus A. This leg, I'm going from height B to height D. So how long is that one? D minus B. So what is left? So I have this one as C minus A, this one as D minus B, and I want to figure out the length. Let's call that L. Pythagorean formula says what? Hypotenuse squared is equal to one side squared plus the other side squared. Okay, side 1, side 2. So hypotenuse squared is equal to one leg, which is C minus A, plus D minus B squared. Well, that was simple enough. Question is, what if you were in higher dimensions? How would you measure distances in higher dimensions? Same thing, distance in 3 dimensions. Just so that my picture does not get too crowded, let me put one of these points to be at the origin. And suppose, so I have one point at the origin, so that simply so that my picture doesn't get overcrowded in 3 dimensions. And the second one, I put some point here and I assume its coordinates are A, B, C. What do you mean the coordinates are A, B, C? Well, consider this X coordinates, Y coordinate, and this one is Z coordinate. By saying this coordinates A, B, C, it means that if we construct the box between so this is the point that we called ABC. Who is A? A is the length of this side of the box. B is the length of this side of the box up to here, and then this one is up to here. What I am interested in is the distance. We said our original point is the point at the origin. What I'm after is this diagonal length. So, two opposite corners of a box are attached to each other. The dimensions of the box are A, B, C. You want to know how long that diagonal line is going to be. That is distance of this point from this point. Well, one way to go about this is to first go to two-dimension and ask yourself, how long is this diagonal? Let's call this one S. This is the diagonal of a rectangle whose length are A and B. So what is S squared? So S is hypotenuse of a right triangle, two legs of which are A and B. So S squared is going to be A squared plus B squared. Is that right? Next, we are going to go ahead, take a look at this triangle. What kind of a triangle is it? What's the relationship between this side of the box and the bottom of the box? It's 90 degrees here. Everybody agrees on that? Okay. So this is a right triangle. Well, what are the specifications of it? This side of it is S. This side of it, that's what we call C. So L is a hypotenuse of a right triangle with the legs S and C. So what do we know about L? L squared has to be S squared plus C squared. Well, what was S squared? It was A squared plus B squared. This is A squared plus C squared. So L so if I want to calculate the length between 2 points, I will figure out how far apart those 2 points are in the x direction, how far apart they are in the y direction, how far apart they are in the z direction. Take each of those, square them, add them up, take square root, and that is how far apart those 2 points are. Let's go ahead and practice. Suppose I tell you, find distance from, so let's consider some point 1 with coordinates 1, 2, 3, and some point 2, say 5, 7, 11. So who's going to play the role of A here? We have gone from 1 to 5. Who plays the role of B? That's a Y movement. I moved from 2 to 7. Who plays the role of C? I have gone from 3 to 11. So 4, 5, 8. So what are we talking about? If you are going from one point to another point, you are moving in 3 directions. Your X has changed, your Y has changed, your Z has changed. You obtain each of those by subtracting the coordinates of the 2 endpoints. Now what do you do with them? Oh, sorry. So what is L? What should I do? Take each of them and square them, just to remind ourselves where they came from. Let me write the subtractions as well. So respective coordinates are subtracted from each other, squared, added up, taken square root, and that is going to give you L. So whatever that is, that's our answer. So 4 squared, that's 16, and then 25 plus 64. So this is 70, 80, and 105. Distance of these 2 points is 105. So if I were to describe, if I want to talk about the length of a vector, okay, so you have some vector, you want to describe the length of it. The best idea you have is right now the length of that line segment, that's going to be the length of your vector. We need some notation. Okay, suppose this is vector v. How do I describe the length of a vector? This is a notation that the book uses. Double vertical bar is used to indicate the length of a vector. In my writing, that might be a little bit too much, so I might just be happy with just a single bar on each side, just like the absolute value notion you had in college algebra. We might just use that in case our formula is getting to be a little bit out of hand. So instead of length of vector, we also call it norm. That's a little bit perhaps unusual for you to call this norm, but that's the official definition. Of course, we have length, we have magnitude, if you wish to call it size, but try to get used to this terminology as well. There are many ways of measuring norm. This is the most common one, and because this is going back to the ancient geometry, sometimes it's called Euclidean norm in honor of those ancient geometers. So another word that is used to describe it, due to the importance of this squaring that you see, and this is really a square root, sometimes it's called the 2 norm. You might suspect that there are in fact 3 norms, 4 norms, infinity norms, and so on. That's a little bit more advanced than what we are doing right now. Okay, this is the length of a vector. So suppose I have a vector. We said we describe vectors with components sometimes. This is a vector with components 3 and 4. Okay, like 3 vectors, 3 steps to the right and 4 steps up. This is the vector I'm looking at. What would be the length of? Somebody said tangent vector. No, it doesn't have anything to do with tangency to it. It's just a vector. Okay, so it's just same notion as the notion of length you had. And how do you get it? You say here, components squared in a square root, and there I go. I might have written my vector in this notation, like 3, 5, 1. Let me make one of them negative so that we have practice with that one as well. What is the length of W? Which is what? Is negative 3 squared, is it minus 9 or 9? Okay, this is one of the most common mistakes. These numbers are in parentheses. So 9, 25, 1, so square root of 35. Whatever this vector is in 3 dimension, its Euclidean length is the square root of 35. So that is a formula for this. So if you had V as AI plus BJ plus CK, or written in our other notation ABC, the length of V is simply given by the same formula you had seen in college algebra. So that wasn't all that bad or all that new. Next issue is, well, what do you mean by angle? So we are doing a bit of geometry, really. We are mixing geometry with linear algebra. Angle between 2 vectors. But if you have 2 vectors, like V and W, you want to talk about the angle between the 2 of them. The easiest way is to draw them from the same spot. So I draw V and W, so this is parallel to that, this is parallel to that, angle between the 2 of them. Not so surprisingly, we are referring to this. This is angle between the 2 of these things. Angle is usually shown by theta. Okay, so we learn a little bit of Greek here. The angle theta is some angle between these two vectors. Any two vectors in general position can be put on a plane, and we measure the angle between these two, and the angle is going to be always measured to be between 0 and pi radians, which is same as 180 degrees. Let's practice some interesting cases, scenarios. If you have a vector v here and a vector w looks like this, you want to call these two vectors as what? V and w are, or what would you say? They are perpendicular. V and w. Well, that refers to the situations where your angle is 90 degrees. What are the other extreme cases? If you had V like this and W like this, what do you think theta is supposed to be? 0. And if you have V like this and W like that, now the angle is a complete 180 degrees or pi radians. Okay, so that is what we mean by angle between vectors. So by now we know what the length is. We know what we mean by angle. Let me just quickly review something for you from trigonometry, which is what do you mean by cosine of an angle? It's a ratio of two things in a certain triangle. What two things are they? Yeah, this is adjacent over hypotenuse. So if you have a right triangle like this, and these are sides A, B, and say C, cosine of theta is what ratio? A over C. So we know who is cosine, hopefully. Next is a very important definition of dot product. Last time we started this thing, but we didn't make that much of a headway. We justified studying this by saying in physics or engineering, dot product is one of the primary objects. If you, for example, force being applied to an object that is displacing by vector d, then F dot d is a very important concept. That is what we mean by mechanical work done by a vector F during this translation. So we have this notion of dot product, but here we are going to formalize the notion for us and explain it a lot more. Suppose I have some vector, let's call it say A, and I have some other vector B, and the angle between the two of them is theta. What do I mean by A dot B? Here is the official definition. What is that? Norm of A times, so length of the vector A. So I find out how long this one is. I find out how long that one is, multiply them, and multiply with something else also, which is cosine of the angle between the two of them. So this is a very important concept we need to practice, and we want to dig into this issue quite a bit more. So let's go ahead, see what are things we want to do. Let's look at some, again, extreme cases. Best way to start studying something is to see, well, what happens in this extreme, what happens in the other extreme, and investigate them like that. Suppose I have some vector A, and the vector B happens to be just a copy of A. So the other guy B just A. So when I am doing a dot product, I'm taking dot of A just with A. Well, what did we say we do? Norm of the first one, norm of the second one, times cosine of the angle between the two. Well, what is the angle between these two? What is cosine of 0? So I'm left with just norm of this times itself. So we get the following interesting identity. Dot of a vector with itself is equal to square of its magnitude. If you take any vector, dot it with itself, you have to get, so who is this one? This is square of length of A. So suppose I give you an example here. Let's take our famous example. Suppose this is my A. What is A dot A? 5. 3 to the right, 4 up. So the hypotenuse is 5. This time, dotted with itself, is the square of the length of the guy. And that has to be 25. So we got this one covered. Another interesting case, suppose I have a vector A. So let's, the other extreme case. Suppose here is my A, and this is my B. What is A dot B? Why? Yes, this is A times B times cosine of the angle. Here we made it clear that the angle is pi/2 radians or 90 degrees. Cosine of such an angle is 0. If this guy is 0, it doesn't matter who the rest of them are. Dot product is going to become 0. So that is another important fact. This is pi/2, yes. Pi/2. Thick pen is hard to write with it. So what we have is that the dot product of perpendicular vectors is 0. And if the dot product is 0, the vectors had to be perpendicular, or one of them had to be 0 to begin with. So we say if dot product of two vectors is 0, it has to be because of either they are perpendicular, okay, like this, or one of them collapse to 0. Like if I had a vector A and my vector B is just one dot. Well, one dot doesn't have any direction, doesn't make any angles or anything. We cannot say that has to be at 90 degrees. Whatever, however, you imagine that dot, if you take that 0 length vector multiplied with A, you are going to get 0 anyway. Next, okay, hopefully we don't have enough time. Let me state our most important result for today. So we have a major theorem. If you have a vector A, which has components A1, A2, say A3, and a vector B, which has components B1, B2, say B3, or as many more components or less components, then A dot B has another description as well. That was our definition. We are going to say there is another way of doing this which avoids this angle, which is the following. Those of you who remember from either Calculus 3 or physics classes, how do you define there, or how do you explain dot of two vectors? You multiply the respective components just the way we did it with matrices, and then add them up, as if this was a row and this was a column, or vice versa. If you were multiplying them as matrices and coming up with a number, you are doing the same thing, except that now we are writing typically both of them in straight lines. So let's practice this. We need to prove this, and that proof requires a law of cosines, and we don't have enough time today to do that, but let's do an example. Suppose I have a vector A, which is 2, 3, minus 1, and vector B, which is 3, 5, plus 8. I ask find angle between A and B. Finding angle by drawing is going to be really hard. Trying to construct these things in 3 dimensions and finding the angle like that is also hard, but what comes to rescue is the fact that previously we had said this is equal to length of A times length of B times cosine of theta. So anytime you want to figure out the angle, you can figure out the dot product like this and divide by the length of the two vectors. So how do we proceed? First of all, we go ahead find A dot B. So 2 times 3 plus 3 times 5 plus minus 1 times 8. And you said you get what? 6 and 15, and minus 8, you got 13. So, but remember, A dot B was also length of A times length of B times cosine of theta. So, who is length of A? Here's my A. How do I get the length? So, square. Don't forget, we don't have any minuses staying over. What is that? Square root of 14. Same story with B. So that's going to be 3 squared, 5 squared. That is, well, just 8 squared. Sorry. Didn't expect this one. What do you want to leave? You can leave. Okay, so I go ahead and calculate B. So I'll have, what's it, 9 plus 25 plus 64. And that is going to give me what? This is 80, 89, 98. And the objective was to figure out the angle between these two. So this is so far is the square root of 14 times square root of 98 times the cosine of the angle between the two of them. Now this supposed to be same as that. And that's the clue that gets you the cosine. So I'll have cosine of theta times square root of 14 times square root of 98 has to be same as 13. So the angle turns out to be 13 over radical 4 times radical 98. And then you go ahead and figure out what this thing is. And then you have to use your calculator on its inverse button. This is called arc cosine or cosine inverse of this quantity. You can combine the two radicals, and of course if you pay attention you can simplify this a little bit.